Hello everyone, this is Dilleswara Rao from Aeronautical department. So last few classes we are discussing on aircraft control system, automatic control system of aircraft lectures we are following from last few classes. So last class we discussed on control system augmentation for pitch and acceleration control system, CAS systems. We have discussed on that. So there we said like where this control system augmentation is being installed in a modern aircraft for making that aircraft stability in in variance with stable condition, and it's helping the pilot to making it in making it in stable condition things only. We have been installed this one for many of the modern aircraft. This is from start from F-16 series in 1970s and 80s. There actually it has been implemented on every aircraft, even in passenger aircraft also it is being installing now. So in addition to that SAS system, that is a stability augmentation system, so this CAS controlled augmentation system also been installed on that. So last class we discussed on pitch rate pitch acceleration and pitch rate feedback system we have considered. Now we will discuss on lateral and directional control augmentation system. We will see it for different types. So see here, the control system augmentation we already said, like, so when a control surface we are operating for making it in pitch up or pitch down, or maybe for rolling movement or yawing movement, we have been using for making that aircraft to turn in a respective region. But this may not be like this may not be like every time higher pitch rates and higher altitude rates we may not get every time. So for that there will be an augmentation system. It's been like, augmentation means it's like a controlling agent only that has been installed in every systems to make that operation in a well precised manner only. So see here the roll and rolling movement or yawing movement for a stable SAS system has been adequate for most of the aircraft, but that maneuverability, that rapid changes of maneuverability for a higher angle of attacks is more redefined in lateral and directional control augmentation system. Because of for a higher angle of attack, to attain the higher angle of attacks and higher pitch higher altitudes, this directional augmentation system also been installed. It is required actually. So the lateral aerodynamic control surfaces like aileron and differential elevators, like elevator is for pitching moment and aileron is for rolling moment, and rudder we will use for yawing moment. So that tend to cause the aircraft to roll about axis which has been designed actually with respect to the body axis of the system. If you see that body axis system again for your reference, so suppose this has been the aircraft model is there. So here the downward will be z axis, and linear will be the x axis, and that pitching moment about the y-axis. That means this is the body axis system that will be used for every aircraft. So here that lateral and directional movement we need to choose for that angle. We need to choose for angle of attack is, that is with respect to the body axis of y-axis and x-axis only. So the rapid that 90 degrees body axis that's been given here, no? So that will gives you the angle of attack with respect to y-axis, that is alpha only. So it is easy to visualize that the angle of attack being converted intermediately in almost entirely to a side slip angle. Like when a side slip angle is when we are introducing the side slip angle for making that rolling movement. So this has been referred as the kinematic coupling of alpha and beta. Like when we are coupling that pitching moment and the rolling moment. That means when it is been pitched up and it has been rolled like that. That means it has been pitched up and rolled like that. Then it will be going positive moment or a negative moment. So that positive or negative moment with the coupling of alpha and this alpha and this rolling moment angle beta. So that is call it as a kinematic coupling of alpha and beta only. So because of the rapid elimination of angle of attack, the body axis for a rolling moment is counter-predictive. So the most of purpose of rolling moment will subsequently generate the required centripetal acceleration, because when it is being side slip like this and if it is making some pitching moment, so it is been turning like that. So while it is turning like this means like you see here. So it has been pitched up like that and it has been slide slip like this. So if it is side slip like this means, so it is getting a centripetal force. That means that is mean like if it is an angle like that, so it will be turn like that. So when it is turning like that means, so required centripetal force for making that acceleration more predictive. So that will be we can get by operating that control surfaces in adequate mode only. So the slide slip created by this kinematic coupling referred to that adverse slide slip only. Because of it will be tend to oppose the roll. That is mean CL beta. So this is CL beta. So it's been normally negative. Like CL beta is been normally when the values of this stability derivative part is negative. So that means the roll will be generate the positive beta throughout the kinematic coupling. Hence that negative rolling moment we will achieve on we will achieve when this kinematic coupling is being installed for making that at a time rolling and pitching moment. So the slide slip angles will be are undesirable for several important reasons. The effectiveness of aerodynamics control surface may be greatly reduced. Greatly, I mean, the aerodynamics effects will be greatly reduced. The directional stability may be lost, so that in some cases aircraft have to known like swap ends in flight, like when the aerodynamic control, like because it is rolling like this and pitching like this means, so it may be like a sometimes pull-up maneuver also it is being going on. So due to that pull-up maneuver and this type of movement, turning moment, so sometimes that swap ends means what is that? Like when this turning moment is going like this, no? So due to that turning moment, it may be lost sometimes that aerodynamic control, like because of adverse gust winds may happen or may happen in forward direction. So that that type of controlling we call it as a swap ends only. So even the directional stability is being maintained, that a large side force can be developed. So that may be the possibly break the vertical tile also, because when it is when it is moving like this, so this vertical tile is there, no, like this vertical tile. So that vertical tile will that will have a more forces, like it will be like more forces it will attain. So due to that more forces attaining by that vertical tile, it may sometimes sometimes it may bend and get distracted also. So that means another important effect we need, I mean, to avoid this one, that occurs during that roll is that roll is been need to be installed here is that that inertial coupling is been installed for making that making to avoid this situation. So suppose that aircraft has been designed to roll around the stability x-axis with no slide slip. I mean, if it is maybe without slide slip, it may not be get a total turning up moment. But if we reduce that pitching moment and making that turning with slide slip, with no slide slip also, if we get a yawing moment like that. So that type of transfers movement also we can achieve. So the transformations can be determined by that body axis system for rolling and yawing rates will be determined by this by the equations that has been given here, no. So that is called the equations given here, that is ps equal to p cos alpha plus r sin alpha, and the resultant for rs will be that side slip s means side slip only. So that will be like minus p sin alpha plus r cos alpha. So another equation that r will be like that resultant force will be like a p tan alpha. So here that alpha is positive because that alpha values should be positive values we need to get, and r and p must have same side, and the alpha is large, so the body axis and yaw rates comparable to that body axis roll rate must be generated. Like when these values, everything the values of r p and r and this alpha has been positive, so that we will get the positive values. Okay, if it is a negative values means what? Suppose that higher values if we get, so that we will get a negative values only, because for a tan if tan 60 is there, or like what is tan 30? Tan 30 will be like root 3 by tan 30 will be like what root 3 only. So root 3 means it's values we are getting positive values only. So like that, if the angles, we may not get that much angle, but when the higher angle of attacks if we are achieving, so the alpha values also should be positive. That means it should be like a 90 minus theta type only. If theta is negative values, like negative movement is getting on, then that positive yaw rate and roll rate we cannot generate from that. So therefore, in the rapid high alpha roll and gyroscopic, like inertia, that gyroscopic means again here the pitching and yawing moment rolls have been, that initial coupling modes have been installed. That will affect that will generate a significant body axis pitching moment. So the Euler equation motion for this inertial coupling for the cross product of inertia can be that can be neglected. So the equations for the pitching moment MIC will be given by like that MIC stand for initial coupling only. So that will be equal to QJ by, so that has been equated to JZ minus JX into PR. So for any modern fighter aircraft with stubby wings means that delta and swept wing swept delta wings, and the engines that are near to the longitudinal axis only, because for every fighter aircraft, I think you've seen that the engine will be near to installed in fuselage itself only. So the moment of inertia JX, like here that JZ and JX will be small. That JX may be compared small with respect to JZ. So the rapid roll about that stability x-axis and x-axis at a large positive alpha can be produced a strong nose-up pitching moment. So to avoid this pitch departure, so the pitch axis should be control augmentation system should be cause that horizontal tail to generate the opposing aerodynamic moment. So like this pitch departure, that pitching moment is being getting of higher values, so that we need to avoid, if we need to avoid that values, so that the pitch axis, where that pitching moment we are occurring, so there we need to augment that system to make that system to operate in lesser values only. Even if it is going for higher values, it need to be get it in lower values only. So that high alpha, it may be difficult to obtain that necessary aerodynamic pitching moment because of that horizontal tail stalling, because that higher alpha values, when previously I said no, when we are getting higher alpha values, so due to that heavier forces acting on that vertical tail, so it may be in a stalling region only. So when even when an adequate pitching moment is been available, so the required yawing moment may be unachievable, because rudder is back-ended by the wings, like rudder is being back-ended by the wings. So the conventional aircraft therefore may have a greatly degraded roll responses at a higher alpha, and that further the control system must often be designed to limit that command roll rate to avoid this pitching departure. Like higher alpha, when we are attaining that higher alpha, so we need to make that radar system, like a vertical tail system, should be withstand that higher loads it has been attaining by that attaining due to that aerodynamic load pressures. Like so when we are giving that command for a roll rate, so that should be in such a way that it has to avoid that higher pitching departure values. Okay, so here that figure, if you see here, so here that this is for CIS lateral directional CIS system. So this figure also you have been, I think you've seen in the SAS system also. In the SAS system again, we have gain the transfer function for ailerons and rudder transfer functions. We have the actuator and the rudder transfer functions have been installed, and that from that transfer function that signal is being transmitted to that that control surface control system. So from that control system, that feedback is being fed into that summing amplifier, so that the based on that feedback only that control system will be operated. And in between that washout transfer function and alpha feedback, alpha rate transfer function, and this bending filters and noise filter thing, and pitch rate feedback also we have given some explanation on that. So based on that only, there will be an instantaneous feedback system that has been given in between that. There will be an outer loop. Inner loop is being created at the summing amplifier. So that the figure illustrates the essential features of a lateral directional CIS system for modern fighter aircraft. The compensation networks, the limiters, and so on are added, which are necessary for that system. So the aileron control channel is been same that has been shown in figure 2. That just now I explained that one. So that except that aileron actuator input, now that cross connection to that radar actuator via an alpha dependent gain. Alpha dependent gain has been given here. No? So that cross connection is known as aileron and rudder interconnector. So if you see that here that gain gain feedback is there. No, so here there will be the aileron rudder loop has been created here. So that loop has been summing up to that amplifier. From that amplifier, that feedback is being given to that total summing amplifier. So that means the cross connection in between that radar actuator via an alpha dependent gain that has been increased. That has been installed here to make that rudder connection. That rudder motion should be augmented with respect to that movement that has been taken by that taken at higher altitude. Higher pitching rates. So that is called that ARI. So that may be implemented hydromechanically in some aircraft and electronically in other aircraft also. So this is for the component of IARE that is necessary to achieve the stability axis roll, because when with respect to yawing and rolling moment, so to avoid that adverse values on adverse values on that vertical stabilizer. So this compensate function will control the control surfaces to aircraft stable at that higher condition. So the ARI gain will be determined as a function of alpha and Mach number. So to achieve that exact amount of yaw rate required to satisfy that constraint equation. So the gain typically estimated from known aerodynamic data, and that has been adjusted to using that nonlinear simulation, because when we are operating that for a higher pitching moment, so we may not get that higher roll rate, higher values for, higher pressure values attained by that vertical stabilizers. So for that, non-linear simulations, like by using that simulation software, we can have a idea on how much forces are been acting on that radar, and how to avoid that control system. How to avoid that forces for getting this roll rate and yaw rate. So we can avoid by incorporating that constant R, function. So that has been R equal to P tan alpha in our steady state trim program, and that trimming of the aircraft will be at a steady state roll. Like when it is getting that rolling moment, also that steady state roll moment we need to achieve. So for that, there will be a separate precise program for that R tan alpha values we can install them that one. So here that figures we have already explained here. So here that see, for the actuator, that gain rate pitching moment is being given here, and there will be a pitch rate function, and that actuator transfer function will be there. So in between that aircraft control surface, so from there that feedback is been summing up through this gain feedback only. So as usual, for an actuator installed for radar also, so that radar has been looped by this gain feedback and internal transfer filter gain feedback also, that has been given to this summing amplifier. And before that, radar rate moment, that roll rate moment, and that separate transfer function for that roll rate moment also been given here to that. And from there, that actual moment has been the actual moment has been given to that summing amplifier. So based on this feedback system only, the actuator, like that roll ARI aileron roll radar interconnector is there, no? So that aileron radar interconnector will control that signal, how much it is been given to that control surface, so that it will be avoid that stalling region of that radar. So for that only, that two feedbacks have been given here. For a feedback, another internal loop also been given here, and there will be like aileron that elevator rate, aileron rate feedback also been summed up here. So by using this feedback, the signal will be given to that radar, and how much values. Here you see that output will be like a pitch rate and alpha, and aileron control output. So what are the values that have been given for this ailerons and elevator and rudder? So that type of outputs will be given out from taking out from this control surface. So here that control augmentation is being if you want to know what are the control augmentation we have installed for this system, other in addition to the SAS system, is this loop only. So if you see that difference between these two loops, you can easily find out that lateral directional lateral and directional CS system. So the table, for the transfer function we have seen shown on there, no. The table shows that angle of attack that almost independent of roll rate only. So, but it is depend upon that pitch rate. So, the second of that table for the pitch rate values have been given here. So, that P and alpha values and beta will be the roll angle, that slide slip angle, and that aileron values, rudder values, and that rudder tile values also we are getting out from. How these values we got it from that by giving that different operating values to that input. If you see here that if you are giving that different values for pitch and the rudder, so for the P and R values are there now here. So for the pitch and alpha values, we are getting this output values only for aileron, rudder, and that rudder tail. So that rate, if it is 5 degrees per second, like if the alpha values, the pitch rate is 5 degrees per second, so that subset provide a higher alpha angle, that has been 6.5 degrees we are getting for alpha. So that pitch rate for 10 and 15 will be used to provide additional data. So that that is depend upon that maximum engine thrust reached between this last two conditions. So the table indicates that stability axis for a roll under that conditions that has been shown for this has been operated at a Mach 0.45, and the required ratio of rudder deflection and aileron deflection will be for a design values of given here, that is minus 0.33 at alpha equal to 2.2 degrees and minus 0.12 at alpha equal to 6.2 degrees. So here the values we are getting for maximum values, for the maximum attaining values, we are getting the alpha values up to that deflection of aileron will be up to this much. So using the additional data for that has seen we have created the data for 0 and 5 degrees, and for 10 and 15 degrees and 20 degrees also. That for that angle of attack that will be showed in ratio of rudder to aileron deflection. So that KRI was the that rudder to aileron that ARI that aileron rudder interaction we have seen that rudder to aileron deflection rate can be expressed with this equation. So that is what 0.13 alpha minus 0.07. So here the alpha will be in degrees only. So in practical design, that Mach number must be first the Mach number of that aircraft must be determined, and the two-dimensional lookup for that table. If you see that KRI, the time and space limitation, that if you find that KRI value with this equation, the design example will not be involved a large variation of Mach number. So the ARI alone would be open to attempt the achievable stability axis roll and improve the improve on that feedback control that has been used to derive that lateral and directional lateral acceleration to 0. So if you see in as in table 1, so the figure 2, here you see that SAS system you see. So here that figure 2 that has been shown that lateral acceleration is a feedback and compare it with that null reference input, and the error signal is being used to drive that rudder actuator. That means this error signal where we are getting when we are getting that feedback from that rudder, it is being summing up to that control surface. From there, that what are the error signal between the feedback and this applied input. So based on that only that rudder actuator will be operated. So this is known as the turn condition scheme. So that and can be used to autopilot system to respond for navigation steering signals, or to relieve the pilot of that pilot of the need to coordinate turns. Like here, when that error signals, based on that error signal, how that turning rate or rolling rate we are deciding. I mean, that has been automatically decided by the system only. So this has been practically we have been feeding up from that response frequency of response of that aircraft control system, and that has been given to this system, so that the system is being operating very accurately, and that we can say it like an autopilot system that has been purely depending upon that electronically operated control systems only. So in the normal acceleration for CAS, that lateral acceleration feedback suffers from a wide variation of sensitivity, because CAS system, you see, for getting that higher values, it is avoiding to making that higher values. I mean, it is avoiding to it is avoiding our aircraft to attain that higher values. So that higher values, if you want to avoid, this CAS system is been more helpful. So that means I mean that for higher acceleration also, that lateral higher acceleration also, it will control that acceleration, so that more stability is being required to aircraft, means we need to achieve this type of values only. So that higher values of feedback gain are needed to needed at low speed, and this may be cause problems with the accelerometer noise, because we said no that the accelerometer noise values have been very high when we are getting a higher pitch rate also. At low speeds like below 0.3 Mach number, the angle of attack, I mean that angle feedback normally use it to use it instead of lateral acceleration. But the disadvantage is that beta sensor is less reliable than that accelerometer. Previously, that significance of stability augmentation, if you see it on previous video, there also we have seen like that accelerometer values we are getting after that. After the maximum values we are attained for that. So based on that only we are getting that maximum values for this beta sensor also. I mean, based on that beta sensor also, that the inner feedback loop in the rudder channel provides a Dutch roll damping by feeding feeding back to that approximation. The studies that stability yaw axis rate in equation 1. In equation 1, if you see, that means this PS equal to P cos alpha plus R sin alpha. So if you see that one, the filtered alpha angle that has been converted into radians has been used to approximate a sin alpha that has been multiplied by the roll rate and subtracted from the yaw rate. So that P and R are roll in the yaw rates only. That the stability yawing axis that has been washed out, so that it is been operates only the transiently and does not contribute to the control error when a steady yaw rate is being presented. So note, the yaw rate feedback is equivalent to yaw rate feedback is equivalent to the combination of beta and beta dot feedback. So beta and beta dot feedback means what? That roll rate and pitching roll and pitching moment, that slide slip and pitching angle inertial coupling is there, no? So it has been it has been related to that beta and beta dot feedback. So the pilot will decide when a when a side slip is required for an aircraft, because of the rudder inputs are applied directly to that rudder actuator. Because when we are getting that slide slip, so actually it may be get that rolling moment and that yawing moment. It's like a together moment is there. So we need to operate that rudder also. How much signal is being given to that rudder, so that it will avoid that stalling region also. We can decide with these things. So the control system will tend to reject that disturbance input, so that desirable effect of limiting that slide slipping capability will be achieved with this CAS system. So this is all about this CAS system that has been installed on that has been installed for controlling that lateral direction and avoiding that higher rates higher, avoiding that stalling region for higher pitching rates and rolling rates. So how to design that, how to avoid that stalling region for the vertical stabilizer, and how to make that system, make that augmented system to control that aircraft in a well manner. We can achieve by this CS system, and that addition of that CS systems also we can explain with some of the examples that in the later classes. In the next class we will discuss on significance of a control system, where with some examples that, examples mean practically installed systems for pitching moment, that directional moment, and that longitudinal moment CA systems also we will see it on later classes. So that's all about this one. So if you have any queries about your things, so you can refer this textbook, and this is all about this lateral and directional CA system. So we'll see it on next slide. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.